Hello, my name is Liz, and I'm going to be doing the second homework for Transport 2. So, I started drawing out the situation. There is a 10 centimeter long uniform cross-section capillary, and it initially contains pure liquid water and deuterated water on its left and right halves. So the H2O goes from 0 centimeters to 5 centimeters, which I have drawn here, and then the DTO goes from 5 centimeters to 10 centimeters. So the other pieces of information that the problem gives us is that at t equals 0.1 seconds, the maximum molar diffusive flux is 2.78 moles per meter squared seconds. So we will use this later. And then it also gives us some of the properties of deuterated water, and that is that the molecular weight is 20 grams per moles and the density is 1,110 kilograms per meters cubed. So first we are looking for the overall mass flux N corresponding to the maximum molar diffusive flux. So overall mass flux N we know is equal to the mass concentration, the total mass concentration, times the total mass average velocity for this situation. So in the problem, we aren't given mass concentration or mass average velocity, so we need to figure this out. So first, let's talk about total mass concentration, which is represented by rho here. So we know that the total mass concentration is equal to the mass concentrations of each of the components added together. So the total mass concentration equals the mass concentration of H2O plus the mass concentration of deuterated water. And we know that mass concentration of a component, so H2O, equals the mass of that component over the total volume. And we know that the mass is of a component is equal to the density of that. So H2O times the volume of the H2O. So now let's try to simplify this further by looking at the total volume. So we know that the total volume is equal to the volume of the H2O plus the volume of the deuterated water. And in this situation, it tells us that it's like split in half. So we have half water and half deuterated water in volume, which you can see depicted in our drawing. So we can write that the volume of H2O equals the volume of DTO, which equals 1/2 of the total volume. So we can plug the 1/2 of the total volume in so that we can simplify it further. So now you can see that the mass concentration of water is equal to the half of the density of water in this situation. And we know that the density of H2O is 1,000 kilograms per meters cubed, which we know is 500 kilograms per meters cubed. And then you can scroll down a little, you can do the exact same thing for the deuterated water. So I'll just rewrite it so that there's no confusion. So this is going to be 1/2 of the volume. These will cancel and you get 1/2 the density of deuterated water, which equals 1/2 of, we are given the density in the problem, which is 1,110 kilograms per meter cubed, and half of that is equal to 555 kilograms per meter cubed. So now we can find the total mass concentration, which is just these two mass concentrations added together. So 500 kilograms per meter cubed plus 555 kilograms per meter cubed equals 1,055 kilograms per meter cubed. All right, so now we have the total mass concentration. So now we want to find the total mass average velocity. So let's first remind ourselves that the sum of the molar diffusive fluxes of each of the components is going to equal 0 here. So remembering that, we can expand this out because we know what our components are. So the molar diffusive flux of water plus the molar diffusive flux of deuterated water is going to equal 0. And we're given that the molar diffusive flux of water is, let me make sure that I did this right, that the molar, yes, the molar diffusive flux was 2.78 moles per meter squared seconds. So 2.78 moles per meter squared seconds. So that means that the other one has to be negative 2.78 moles per meter squared seconds. So now, So now let's look at the equation for molar diffusive flux, which it's going to be the molar diffusive flux of a component I is equal to its molar concentration times its velocity of the component I. And then we can use the equations for the concentration, the molar concentration, which is the moles over the volume. Just like mass concentration is the mass of the component over the total volume, we have molar concentration is the moles of the component over the total volume. So that makes sense. So then to find moles, we can do the mass of component I over the molecular weight of the component. And we know that this gets moles because if we think about the units, this could be like grams over grams per mole, and that's just gonna end up being moles. Great, so now we can plug this moles into this equation and then plug the molar concentration into the equation for molar diffusive flux, and then we can use the molar diffusive flux that we're given to solve for the velocity of the components. So let's see, we have room over here. So let's go ahead and plug these in. So we get molar diffusive flux equals the, we have Ni over V times Vi. So the Ni over V, which is moles over volume, we know that moles equals mass over molecular weight, so let's plug that in. So we have mass over molecular weight. And then, excuse me, all of that over the volume. So we just plugged in this into here. And that is plugged into CI which is the molar concentration, and then all of that times the velocity of the component I. Yes. So next, we can just plug in the numbers that we know. So we know that, oh yes, I remember. Scroll back down, sorry. So let's look at the molar diffusive flux of H2O. So we know that the mass of H2O we did up here is 1/2 of, well, 1/2 of the volume times the density of H2O, because it's the density of H2O times the volume of H2O, which can be simplified to this. So let's go ahead and plug that in here. And we know that the density of H2O is 1,000. So let's plug that in. So this whole thing here is equal to the MI here, so the mass of the H2O. And then we know that the molecular weight of H2O is 0.018 kilograms per mole. Oh, I'm so sorry. I'm writing over into the picture. So I'll review this since it was, my face was covering it, but we have the 1,000 kilograms per meter cubed, which is the density of water, times half of the volume, which is going to equal the mass of the water, divided by the molecular weight of the water, which is 0.018 kilograms per mole. And then that divided by the volume, and then, divided by the total volume, and then times the velocity of H2O. So we know that the molar diffusive flux is 2.78, and we can then solve for the H2O, the velocity of H2O. And I already calculated this into my calculator, and it's going to equal 1.0008 times 10 to the negative 4th meters per second. And that's because we can simplify it so that we just do 1/2 times 1,000, which is 500, divided by 0.018, and then we can do 2.78 divided by that number, and then we get the velocity of H2O. So that means that the velocity of the deuterated water is going to be negative 1.008 times 10 to the negative 4th meters per second. So, yep. All right. So then, we can do the, then we can look at the equation for the total velocity. So the equation for the total velocity is just going to be the mass fraction of water times the velocity of water plus the mass fraction of deuterated water times the velocity of the deuterated water. And this makes a lot of sense because we are looking for the total mass average velocity, and so we need to consider the mass fraction of the component times the velocity of that component, and all of the those for each of the components added together to get the mass average velocity. So then we can let's also remember that the mass fraction equals the mass concentration of that component. Equals the mass concentration of that component over the total concentration. And we know this because this equals the mass of component I over the over the total volume, and this is going to be the total mass over the total volume, which we remember from doing up here, where we have the mass concentration of H2O equals the mass of H2O over the total volume. And then these will just cancel, and then you get the mass of the component over the total mass, which we know is the mass fraction. All right, so then we can plug that in. Let me erase this. I don't know why this is here. And we get and then we can just plug in all of the numbers that we know. So we know that this is 500 kilograms per meter cubed over 1,055 kilograms per meter cubed times the number that we just calculated, which is 1.0008 times 10 to the negative fourth meters per second, plus our mass concentration for deuterated water over the total mass concentration that we calculated before, times the negative 1.008 times 10 to the negative fourth meters per second. So now we get our total mass average velocity, which is negative 5.27 times 10 to the negative 6 meters per second. And now we have our unknown variables to plug into our original equation to find the overall mass flux. And we know that's corresponding to the max molar diffusive flux because we used that here. So let's plug the numbers into mass flux equals mass concentration, total mass concentration times the total mass average velocity, and we are going to get I already calculated these two numbers multiplied together, and I got negative 5.56 times 10 to the negative third kilograms per meter squared seconds. All right, so let's now look at the second part of this problem. So the second part is to make an order of magnitude estimate for the maximum driving force for diffusion at t equals 0.1 seconds. And as a reminder, at 0.1 seconds, the max molar diffusion flux is 2.78 moles per meter squared seconds. So first, let's look at the equation for the driving force. And I wrote that down here. Let's make us some more room. Oops. All right. So let me get my pen. All right. So the driving force, that's what the little d represents, is equal to the sum of the components. So the molar fraction of component I times the molar diffusive flux of component J, so the opposite there, minus basically the inverse of that, so the molar fraction of component J times the molar diffusive flux of component I. And then all of that over the molar concentration times the Stefan-Maxwell diffusivity, which is represented by this fancy capital D right here. So let's go ahead and expand that out. So we have two components, so it's going to look like this. I'm basically just going to replace all the I's with 1s and all the J's with 2s. Great. So now that we have that expanded out, we can also simplify it down more by remembering from earlier when we talked about how J1 equals negative J2. So basically, the molar diffusive flux of one of the components is equal to the negative of the molar diffusive flux of the other component. So we know that, and then another thing that seems obvious but we often forget is that the molar fractions are going to add up to equal 1. So we can also write this as x2 equaling 1 minus x1. So if we replace all of the negative, or all of the J2s with negative J1, so we can also write this like this, and all of the x2s with 1 minus x1, then we'll have everything in terms of J1 and x1. And then obviously the concentration of the molar concentration and the Maxwell diffusivity. So let's go ahead and do that. So like I said, the x's are the molar fractions and the j's are the molar diffusivity, molar diffusive flux. So we have x1 and then times negative j1 minus 1 minus x1 times j1. All right, so now we have simplified it down a lot, so a lot of the stuff can really end up looking a lot prettier. So this will simplify down to negative the molar diffusive flux of 1 over the molar concentration times the Stefan-Maxwell diffusivity. So then, let me think for a second. Okay, great. So now we have it simplified down. So really all we need to do is find the concentration and what the Stefan-Maxwell diffusivity is. So Stefan-Maxwell diffusivity is the simple one because this is an ideal system. So the diffusion coefficient is going to be equal to 10 to the negative 9th meters squared per second, which that's just something that we know, that we just like memorize because this is an ideal system, so that's really handy to know. And then for the concentration, the molar concentration, we need to do moles over volume because that's how you get molar concentration. So let's find the moles of each of the components, which we know is going to be the mass times the 1 over the molecular weight. So basically the mass divided by the molecular weight gets you the moles. So 1,000 kilograms per meters cubed times 1 mole over. One, 0 kilograms per meter cubed. So this 1,110 kilograms per meters cubed and the 1,000 kilograms per meters cubed are the densities of D2O and H2O, which is given in the problem, which we talked about in part 1. And you might be wondering why I'm writing down the per meters cubed, but it will make sense in a moment. So now we don't know the exact volume, but we're just going to divide it by 2 because we have the moles of we have the moles per meter cubed of the H2O, which is represented right here. And then this is the moles per meter cubed of D2O. Here, let me move it down a little bit more. I just realized my camera's kind of in the way. Sorry. There we go. All right. So we have those moles per meters cubed, and since we have 2 components and they're taking up equal volumes, we're going to divide it by 2. So we're just kind of going to assume that they're each taking up a meter cubed, which will cancel out like these meter cubed on top here. So that's why we're dividing it by 2. So that I already did the calculation, and that's going to equal 55,527.5 moles per meter cubed. Great. So next, we have the molar concentration and the molar diffuse and the 7 Maxwell diffusivity. So we can go ahead and plug it into this pretty simple equation, and we know that that the molar diffusive flux at t equals 0.1 seconds is 2.78 moles per meter squared second, because that was given in the problem. So I'm going to type that in, or write that in here. And then we have the molar concentration. And then we have the 10 to the negative 9th meters squared seconds for the 7 Maxwell diffusivity. So I also did that calculation already, and I got negative 5.0065 times 10 to the 4th. And then, so that's the driving force. And since we're looking for the estimate, the magnitude estimate, we can say that the driving force magnitude estimate is 10 to the 4th. So that is the answer for part 2. Alright, so let's talk about part 3 now. So part 3 is to sketch the initial, intermediate, and final mass transport profiles. So I have the grids below, but it's going to be at t equals 0.1 seconds, 60 seconds, and at infinity. So let's go down to the grids. All right, so I'm going to do my best to draw these. So first is the mass concentrations of H2O and D2O. So we know that it's given in the problem that the densities of H2 or D2O is 1,110 kilograms per meter cubed, and H2O we know that it's 1,000. So, and this is the positions. So for all of the grids, it's going to be, this is going to be the x-axis. So the capillary is 10 centimeters long. So 5 centimeters is where the divider is initially, and since the initial is t equals 0.1 seconds, that's like right when the divider is removed. I'll go ahead and write in the other one. So intermediate is at 60 seconds, and final is infinity seconds. So we know that for right at the point where the divider is removed, there is water on the left side from 0 centimeters to 5 centimeters, and then there's D2O. Did I say right side? On the left side from 0 centimeters to 5 centimeters, and then there's D2O on the right side from 5 centimeters to 10 centimeters. So we can show that. Here, I'll make H2O be blue. And then right at the divider, this is going to go down to 0 because there's no water on from 5 to 10 centimeters. And then for D2O, it's going to be 1,110 centimeters, so it's a little bit higher than the 1,000. But on the left side, from 0 to 5 centimeters, there's no D2O, just like explained in the initial problem. So then, once the divider is removed and 60 seconds go by, that is when we get some mixing. So it's going to look like we have still a lot here of D2O on the right side. However, let's see, where is my kind of, so it's still gonna do this. This is my best drawing. And then the H2O is going to look like this. So we start to get some mixing. So there's still more D2O on the right side and more H2O on the left side. And right at the divider, the slope is greater because it's dispersing out from that divider, basically. So that's why the lines are curved, because it's steeper, like the slope is steeper at the divider. So that's what it's like at t equals 60 seconds. Then at t equals infinity, it's going to be completely dispersed and diffused, and it's going to be like at an equilibrium, so it's going to be all well mixed together. So that means that the density of the water is going to be even across every position. And remember that the x-axis and the y-axis are the same as this first initial graph. But the density is going to be at 1,000 for water, and then for D2O, it's going to be at that 1,110 point. But it's going to be like that across the whole capillary, because now they're all mixed together. Okay, so let's move on to the next one. So I changed the y-axis to fit what we found for the answer for, or what we found while doing the problem. So this is in thousands. So we had that the molar concentration is, for both of them, is about 55,000. For D2O, it's just slightly higher, but I'm going to kind of draw them as pretty close to the same. So again, the water is at 55,000 moles per liter at the beginning from 0 to 5 centimeters, and then there's none of it from 5 to 10 centimeters. So this is still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is in centimeters. So it's for the same reason as the initial one of the mass concentration. And then the molar concentration of the D2O, it's going to be all on the right side, and there's going to be none on the left side, just like as stated in the problem. And then again, it's going to do the same thing as the mass concentration, and it's going to sorry, this is not very curved. Maybe I can erase this line I didn't mean to make. There we go. So that's for the D2O. Same reasoning as the intermediate graph for the density or the mass concentration. But now we have it at starting... sorry, my drawing skills are not the best. But you get the gist, I hope. So these should be equal and opposite, except very slightly different. But anyways, so again, right at that dividing point at the 5 centimeter point, the slope is going to be a little bit greater because that is where they're mixing together. And there's still going to be more D2O on the right side and more H2O on the left side in moles. So that's why for the molar concentrations, that is how it's shown. And then for the final, again, similar to the graph above it up here, it's going to now be even throughout. It's going to be all mixed together. Same reasoning as before. All right, next. So next we have the molar diffusive flux. And in the problem it says that at t equals 0.1 seconds, the max molar diffusive flux is negative 2.78 moles per meter squared seconds. So for water, which is blue, at the 5 centimeter point, it's going to be at 2.78 because that is where the max diffusive flux is at t equals 0.1 seconds. It's going to be at that where the divider was removed. So that's for water, and this is like the slope is going to be really steep because the divider was just removed. So this is like right after it was removed, and it like just barely started diffusing. So and then on the left side, there's not going to be, it's going to still be at 0 diffusion because this is like right when it started diffusing. And then same goes for the right side. it's going to be at 0 because it hasn't started diffusing yet. And then similar reasoning for D2O, except D2O is going to be negative 2.78 because, like we said, the negative J1 equals J2, like we talked about at the end of the last part of the problem. So the molar diffusive fluxes are equal but opposite. But same reasoning as for H2O. Then for the next graph, it's going to look similar, but it's going to start diffusing. So I have the red, so it's also going to be a little bit less than the negative 2.78 mark, because that was the max molar diffusive flux right at t equals 0.1 seconds. It was described as the max molar diffusive flux. So we know that it goes down a little bit, and then as it goes down, it's dispersing more. So it's going to have that same curved, like this. For the similar reasoning as above. So this is going to be a little bit below 2.78 for the H2O. So yeah, that's that graph. And then finally, let's see if I can move it over more. Sorry if my head was in the way before. If you couldn't see either of these graphs before, this is what they look like. And then for this one, it's going to be the molar diffusive flux is going to be at 0 because it's not diffusing anymore. It's all mixed together. So for both of them, it'll be 0. So I'll just draw that out here. And this is at 0. All right. So last one we have, oops. The last one we have is the molar flux. Or I'm sorry, overall mass flux. So this is overall mass flux, so it's not H2O and D2O. I'm just going to draw it in the black pen. And this is going to be at the negative 5.5 times 10 to the negative third kilograms per meter squared seconds. And this was the answer to part number 1 that we found. So at 5 centimeters, it's going to be that number, and then everywhere else, and then it's going to curve to 0 everywhere else, like that. For similar reasons, it's just started to diffuse, so the molar flux, it just started to move, I should say, away, like at that divider. So that's why it's at position 5 centimeters. And then the overall molar flux is going to be smaller at that 5 centimeters because now it's spreading out more. So the overall flux, overall flow of everything is going to decrease. But everything else, it's still going to be at 0 on the ends at 60 seconds because it's still working towards there. So we're just going to make it the overall molar flux at 5 centimeters is going to be closer to 0. And then it's starting to even out. So then at t equals infinity, the molar flux is going to be, the overall molar flux is going to be at 0 because now it's all dispersed and there's doesn't need to be the movement between the two components, because it's kind of like, well, there still will be movement technically, but it's kind of like at equilibrium, so no like overall movement. So yeah, it's going to end up being at 0 for the overall molar flux at t equals infinity seconds. And that is all of the graphs. I hope you enjoyed my drawing skills. Here, I'll zoom out so that you can see all of them together at once. But yeah, that's the end of this problem. Thank you.